17.3 Factors influencing the storage and movement of groundwater. Summarize the factors that influence the storage and movement of groundwater. The nature of subsurface materials strongly influences the rate of groundwater movement and the amount of groundwater that can be stored. Two factors are especially important: porosity and permeability. Porosity. Water soaks into the ground because bedrock, sediment, and soil contain countless voids or openings. These openings are similar to those of a sponge and are often called pore spaces. The quantity of groundwater that can be stored depends on the porosity of the material, which is the percentage of the total volume of rock or sediment that consists of pore spaces, figure 17.9. Voids most often are spaces between sedimentary particles, but also common are joints, faults, cavities formed by the dissolving of soluble rock such as limestone, and vesicles, voids left by gases escaping from lava. Figure 17.9 Porosity demonstration. Porosity is the percentage of the total volume of rock or sediment that consists of pore spaces. Variations in porosity can be great. Sediment is commonly quite porous, and open spaces may occupy 10 to 50% of the sediment's total volume. Pore space depends on the size and shape of the grains, how they are packed together, the degree of sorting, and, in sedimentary rocks, the amount of cementing material. For example, clay may have a porosity as high as 50%, whereas some gravels may have only 20% voids. Where sediments are poorly sorted, the porosity is reduced because the finer particles tend to fill the openings among the larger grains. Most igneous and metamorphic rocks, as well as some sedimentary rocks, are composed of tightly interlocking crystals such that the voids between the grains may be negligible. In these rocks, fractures must provide the porosity. Permeability, Aquitards, and Aquifers. Porosity alone cannot measure a material's capacity to yield groundwater. Rock or sediment may be very porous yet still not allow water to move through it. The pores must be connected to allow water flow, and they must be large enough to allow flow. Thus, the permeability, permeare equals to penetrate, of a material, its ability to transmit a fluid, is also very important. Groundwater moves by twisting and turning through small interconnected openings. The smaller the pore spaces, the more slowly the water moves. This idea is clearly illustrated by examining the water yielding potential of different materials in Table 17.1. Here groundwater is divided into two categories: 1. The portion that will percolate downward under the influence of gravity, called specific yield, and 2. The part that is retained as a film on particle and rock surfaces and in tiny openings, called specific retention. Specific yield indicates how much water is actually available for use, whereas specific retention indicates how much water remains bound in the material. For example, the ability of a clay deposit to store water may be great, due to high porosity, but its pore spaces are so small that water is unable to move through it. Thus, the clay's porosity is high, but because its permeability is poor, it has a very low specific yield. Table 17.1 Selected values of porosity, specific yield, and specific retention *. Impermeable layers that hinder or prevent water movement are termed aquitards. Aqua equals water, tard equals slow. Clay is a good example. On the other hand, larger particles, such as sand or gravel, have larger pore spaces. Therefore, the water moves through with relative ease. Permeable rock strata or sediment that transmit groundwater freely are called aquifers. Aqua equals water, fer equals carry. Sands and gravels are common examples. In summary, porosity is not always a reliable guide to the amount of surface water that can be stored as groundwater, and permeability is significant in determining the rate of groundwater movement and the quantity of water that might be pumped from a well.